Math Made Easy with PDY. Kindly subscribe, like, and share the videos you've been watching. And if you also want to personally get in touch with me, you can link me up on my WhatsApp lines as shown on your screen. You can equally get in touch with me, live stream lessons on Telegram, and you can channel your questions through the same channel with name Math Made Easy with PDY. Thanks so much for your support, and then God richly bless you. Without wasting my time, we are going to have another episode on the lesson Plane Geometry 2, which we caption it as Circle Theory. We have taken one example already. We've taken the first part. Now we are continuing. In our previous lesson, we actually looked at the angular properties of circles, which include what we call the arrow theorem, we also had the bow theorem, as well as the cyclic quadrilateral theorem, and then finally we looked at what we call the semicircle theory. We'll just do a recap of it before we move on to today's lesson. So with the help of our Geogebra board, we found out that this is the nature of the arrow theorem, and it defines as twice the angle subtended at the circumference of the circle equals the angle subtended at the center of the circle, on condition that they subtend on common points or common chords or common arc. That is what we learned over there. And you realize that per the nature of this diagram, we can shift the arrow from one end to the other. But remember, the angle formed at the circumference of the circle remains intact. For instance, I have angle CDB, which is 39 degrees, 39.9 degrees. When you multiply that value by 2, it gives you the angle at the center, which is angle CAB, which is 79.81 degrees. That value also is intact. So when I shift the point D from any point on the circumference of the circle to any other location, you realize that the value does not change. It remains intact. Now let's observe something here. When I increase the angle subtended at the center, you realize that it will be changing, and automatically the value of the angle at D, which is at the circumference of the circle, also keeps on changing. So half of the angle at the center equals the angle at the circumference of the circle. Please take note of this, and that is why we say that is the arrow theorem. Again, twice the angle at the center, at the circumference of the circle, equals the angle at the center of the circle, on condition that they subtend from common points or common chords or common arc. So the arc is CB rather. And then if I should have introduced a line segment from C to B, it still makes it intact. So the angle, either they subtend from common points, which is C and B, or subtending from common arc, CB, or common chord, CB. And that is the arrow theorem. Again, the arrow theorem can be in another form, which is shown in this diagram. And that is, just carefully have a good look at this. I have the reflex angle at the center of the circle. So reflex angle CEF, it's having a value of 236.79 degrees, as you can see. Now we have another angle subtending at the circumference of the circle. That angle is angle GHF. There is a relationship between that angle and the one at the center of the circle. Hence, let's look at something here. When you multiply the angle 118.4 by 2, it equally gives you 236.79 degrees. If I shift the point H from its current location to any point on the arc within the minor segment, you realize that the angle still remains intact. It remains intact. But observe something here. When I shift F and move it a little bit away, you realize that the reflex angle becomes wider. So when it becomes wider, you have 213.67 now. Now, if you divide that value by 2, you realize that you'll be earning 106.83 degrees. So this is a relationship here. Don't confuse this concept here with what is shown as the cyclic quadrilateral. They are not the same. They are not the same. So this is a recap of what we did in our previous video. And then we came on to the cyclic quadrilateral theorem, which we said that per the cyclic quadrilateral theorem, the quadrilateral must have its vertices, all of them, on the circumference of the circle. So I have the vertices of this quadrilateral as P, R, O, and Q. Now, the angles opposite the vertex, the two vertices are actually what? Summing up to give us 180 degrees. So that is what we found out in our previous lesson. So it means the angle POQ or PQO is giving us a value of 100.67 degrees. Angle PRO is giving us a value of 79.33 degrees. When you add these two values together, automatically gives you 180 degrees. Again, angle QPR is 83.17 degrees. Likewise, QOR is 96.83 degrees. When you add them up, you get a total value of 180 degrees. Then when you put all the angles within the cyclic quadrilateral together, you must also end up getting 360 degrees, because one of the angular properties of all quadrilaterals, the sum of the interior angles add up to 360 degrees. So just imagine shifting R from its location to another very close to P, but you realize that this is what is happening. The opposite angles for P and O are changing, but that of R and Q are not, because they are fixed and they still sum up to what? 180 for the opposite angles, and then the sum of the interior angles altogether is 360 degrees. Then we moved on to the semicircle theorem, which we said that if you have a diameter dividing a circle into two equal halves, any angle that subtends on the diameter at the circumference of the circle is exactly 90 degrees, exactly 90 degrees. So you realize that the angle V, which is the angle subtending on the diameter TU, it's giving me an angle of 90 degrees. It is fixed, it doesn't change. So that is another thing you must bear in mind. Then the last one, as I said, was the bow theorem. So you can just look at this shape here. You have the bow theorem or the bow tie theorem. Now with this theorem, then we say angles subtending on common points or common arcs or common chords within the same segment at the circumference of the circle, they are equal. So we have angle MKJ. If we consider MJ as the arc or the 2 points, and then K and L being within the major segment, automatically the angle at K and the angle at L must be equal. And likewise, the angle at M and the angle at J should also be equal. if they subtend from the points K and L or the arc KL. So look at something very interesting here. When I shift K and move it closer and closer to L, you realize that it fits perfectly onto it. That's why we always say that these two angles, they actually equal. They are actually equal. Again, I can move M from wherever it is and move it straight to meet J, and you realize that it also equally fits perfectly. So that's the basic conditions we considered in our previous lesson for circle theorem. So we are moving on to the other theorems. So to begin with, the first theorem I want us to consider today is the radius tangent theorem. Now, what does a radius tangent theorem define? It actually tells you the relationship between a radius intersecting a tangent. Remember, in our previous lesson, we looked at what a tangent is. We said a tangent is a straight line drawn in space to touch an arc at a point of tangency. So now, when any radii or any radius intersects with a tangent, it forms automatically an angle of what? 90 degrees. It forms an angle of 90 degrees. So let's use our GeoGebra to confirm this theory. So with the GeoGebra, you realize that I have a circle drawn, and then it has center O, and then it has a tangent AB. And if you look at it carefully, you realize that the radius OA intersects the tangent AB at an angle of 90 degrees, which is formed at A. So I can even send the point A round the circle, and interestingly, it's still going to remain as an angle of what? 90 degrees. It will never change. It will never change. So that is why we always say that when a radius intersects an angle, intersects a tangent, it meets it at an angle of what? 90 degrees automatically. Not radius alone. Remember, we can extend O to give us a diameter. So when you also equally have a diameter intersecting a tangent, they meet at an angle of 90 degrees. They meet at an angle of 90 degrees. So that is about the radius tangent theorem. Then to the next theorem, we have the dual tangent and radius theorem. Dual tangent and radius theorem. What do we mean by that? We are looking at intersection between two tangents and two radii on a circle. Now, when two tangents and two radii intersect, now there are a lot of angular properties they depict. In the first place, we considered a radius tangent theorem, which is when a radius intersects a tangent at a given point of tangency, they form an angle of 90 degrees. So in the first place, when you have two tangents meeting two radii, then in other words, you are getting the 90 degrees angular property coming on board. Now, at the end of it all, you realize that the shape looks like a quadrilateral, or it is a quadrilateral. Now, so with my diagram here, it depicts that TB is a tangent, TA is also a tangent. Now, it is seen that TB is equal in size in terms of dimension to TA. They are of the same length. And remember, the OB is a radius, and then OA is also equally a radius. So in other words, if the length of the tangents are equal and the two radii are also equal, then it means that the whole shape is giving you something like what? A kite. Because it's a kite that has that property, whereby two adjacent sides are equal in size. And therefore, again, when you draw a straight line from the center to meet the point of intersection between the two tangents, it is also believed that the angles subtended at the center and the point of intersection of the two tangents will be divided into two equal halves. Hence, when it divides it into two equal halves, then we say that the two triangles formed by the intersection between the two radii and then the tangents They are congruent. They are congruent. Let's verify these angular properties with our GeoGebra. So coming to our GeoGebra, you realize that I have DC and then DB as my two tangents, and then OC and then OB as my two radii. And the intersection between the line OC and then CD, which is the tangent, they intersect at an angle of 90 degrees. And you can actually see that is the angle alpha here. And then angle beta is the intersection between the radius OB and then DB, which is the tangent. And therefore, it also forms an angle of what? 90 degrees. Remember, we added some other angular properties to it, whereby we said that the length of DC, which is the two tangents, and then DB, they are equal in size. Now, let's take the measurement for DC, and then let's see. So, taking the distance of DC, you can just observe it. DC is perfectly 6.06, and likewise, taking the dimension of DB, it is also 6.06 degrees. It's also 6.06 degrees. Again, we also said that when you draw a straight line from the center to meet D, which is the point of intersection between the two tangents, the two angles formed over there will be divided into two equal halves. But before that, let's measure angle. Let's measure angle CO. Let's take it again. So we are measuring angle DOC. When we measured angle DOC, showing an angle of 120 degrees. Likewise, let's measure angle BD. Let's take it from the other end instead. So CDB. So that is another angle formed there. Let me show it clearly. So that is also 60 degrees. So here is 60 degrees, and that is 120 degrees. The two angles add up to what? 180 degrees. Likewise, the two angles here, intersection between the radius and tangent, which is 90, another 90 there, we also have it as 180 when you sum them up. So ideally, it means that when you add up the opposite interior angles, when the two tangents and the two radii intersect, you should get an angle of the opposite angles adding up to 180. Likewise, the sum of all the interior angles should also give us 360 degrees. But what I wanted us to know was much with respect to when a straight line is drawn to divide the angle subtended at the center to that of the tangent. We wanted to find out what angular property is depicted there. So let me do away with the angles at alpha and then the opposite angle. Now let's measure COD, just COD alone. COD. So angle, let me take it as C. We are measuring. So angle CO is taken from the reflex. So let's take it from the other way around. DOC. So angle DOC, if you look at it carefully, it is showing an angle of 60. Remember, the full angle COB was 120. So just measuring, drawing a straight line to divide the center O to D into two equal halves, it means you are getting an angle of 60 here. Again, remember the full angle at D was 60. Let's find out if we measure the angle CD and then O. CDO, let me show it clearly to you. What value is it showing? It's showing an angle of 30 degrees. So it tells you that when any straight line is drawn from the center of the circle to meet the point of intersection of the two tangents, it divides the angles there into two equal halves. So these are the angular properties we've actually verified with respect to the dual tangent and dual radius intersection. So please take note of that. Then again, we look at the next theorem, which is the alternate segment theorem. The alternate segment theorem. What does the theorem talk about? The theorem actually looks at the connection between a chord and then a tangent. A chord and then a tangent. Now, when a chord and then a tangent intersect, when a chord and then a tangent intersect, now, in the first place, let's consider a chord alone. We find out that a chord is any line that is drawn to connect 2 points on the circumference of the circle. So with my diagram here, if I have the chord as BD, now the chord BD has partitioned the circle into 2 segments, the deep blue section and then the royal green section. The deep blue section and then the royal green section. Now again, when you have any angle formed between the chord and then any tangent, then an angle will be formed between BD and C. Remember, my ABC is a tangent, and the tangent, they meet the chord at the point B. Therefore, when you have a chord intersecting the tangent at B, we have an angle formed within the smaller segment. Now, in the major segment, no angle has been formed yet, but if you draw any straight line to subtend at the circumference of that major segment on that chord, automatically the 2 angles there must be equal. The 2 angles there must be equal. Then again, we can say that if we take BE to be our chord, if we take BE to be our chord, now BE will have an intersection with our tangent ABC at B. And in this case, that is also going to form another angle in one segment. So in other words, let me just make a small demonstration here with a yellow color. So it means that this section here becomes the minor segment, and from E all the way to meet B becomes angles within the major, or becomes the major segment. And in this case, the angle subtended by EDB on that chord EB becomes an angle which is equal to EBA. EBA. So the angle formed here, if I call it theta, any angle subtending on the chord BE in the major segment will automatically be equal to theta. So whereas theta is going for the, so we say this is the alternate segment, the other segment. Alternate means other. So the other segment theorem. The other segment theorem. And this theorem only comes on board when there's a connection between a chord and then a tangent in circles. A chord and then a tangent in circles. So please take note of that. So if here the angle BDC is alpha, then the angle BED it's also going to be labeled as alpha. So let's confirm this theorem from our Geogebra. So from our Geogebra, now you can observe that we have a circle with center A. Circle with center A has a tangent GF on it, and therefore the tangent GF intersects or meets the circle at the point D. At the point D. So in this case, having all these angles available, I've measured all of them so that it just goes directly. It wouldn't take much of our time. Now, if I should consider the angle EDF, the value is approximately 65.06 degrees. EDF is 65.06 degrees. And then the value of ECD is also 65.1 degrees approximately. Now, you realize that if I approximate it to the nearest 1 degree or 1 decimal place, actually you are going to obtain the same value, 65.1 degrees, 65.1 degree. Then and again, going to the angle CED, which is 54.02 degrees. Coming to the other, we have CDG, that is 54.06 degrees. So in this case, we say that what then is the alternate segment? The angle at E, its alternate segment is 54.06 degrees, which is found as G, D, and C. So that is the angle there. So please take note of this. Now, the chord CD has partitioned the whole circle into 2 segments. And the first segment is the minor segment here. And then the major segment is the whole of this big section here. That's the major segment. So when any angle subtends on this major segment at the circumference of the circle with the chord CD, which makes an angle with the tangent CGF, then it means that the 2 angles must be equal. Again, if I should have taken my chord to be DF, DE. So if we should take it as DE, and then DE makes an angle within the minor segment to the tangent GF, then we say that an angle formed here is actually what? Equal to any angle that subtends on the chord DE in the major segment. And the only angle formed in the major segment is the one at C. So I can shift C very close and close, but still the angular property is the same. It doesn't change. Please take note of that. We want to verify these angular properties, not that you just learn that, okay, angles in the alternate segments are equal and therefore this is how it is. No, you should know when to apply which one of them at what point in time. So take note of all these things. Then and again, in some cases, they may ask you to find the angle CDE. So which is the angle that I've labeled as lambda here. So in this case, that angle is 49.747 degrees. 49.47 degrees. Because it gives us a straight line angle here. So whatever I have here plus whatever I have here, subtracting from 180 will give us that angle altogether. So please, that is how the alternate segment angle theorem also holds. Then to our final theorem we want to look at, which is something obviously you do know already, but we want to also say that when it comes to circles, you may have such a theorem in there automatically. Now we have the isosceles triangle theorem. The isosceles triangle theorem. And what does it state? When you have any 2 radii intersecting a chord, automatically you have an isosceles triangle formed. Because remember, 2 radii are equal in length. So when you have any chord intersecting it, it gives you an isosceles triangle. So That is about the isosceles triangle theorem. Let's verify that with the GeoGebra. So with the GeoGebra, you realize that I have my center of the circle as A. The points B and C are points on the circumference of the circle. And I've joined A to B with a straight line, and then A to C with another line. Now, the chord BC connecting A forms a triangle, and you realize that it gives me a perfect isosceles triangle here. So I've measured angle ABC, which is 34.07. Likewise, angle ACB is also 34.07 degrees. I can widen it up and the values will change, but when the two values changes, it doesn't mean they are different. They are the same, because it gives you the two angles to be equal. Please remember that if you want to determine which angles are equal, then it means you must consider where the angle is facing. The sides too must be equal. So this angle as C, it's watching directly. Look at something here. If I should make a small sketch, it's watching directly the line AB, which is a radius. And therefore, any angle that also watches the same line AC, for which we can see that is beta here. If I should go for a different color, then beta is going for that. Remember, AB and AC are equal in length because they are two radii altogether. So their angles must also be equal. So in a nutshell, these are the major angular properties when it comes to the circle theorems. These are the major angular properties you need to know very, very well when it comes to the circle theorem. And to go through fast with you, we have sum of all angles in a triangle equal to 180. It's something you shouldn't forget. You are going to need it when we start solving questions on circle theorem. Then you have the isosceles triangle theorem, whereby the base angles are equal in size. Then parallel lines, when it comes to parallel lines in circles, the alternate angles are equal, which is the Z angle. Remember, this is different. Point 3 is totally different from alternate segment theorem. Even though it states that angles in the alternate segments are equal. Likewise, alternate angles are also equal. But remember, this is totally different from alternate angles in parallel lines, even though they are all equal. Then we also had cyclic quadrilateral. The opposite angles are supplementary, meaning that they add up to 180 degrees. Then angles at the center, twice the angle at the center, twice the angle at the circumference gives you the angle at the center. And this is where we gave it the name, the arrow theorem. This is why we call it the arrow theorem. The arrow theorem. That's the arrow theorem. And then angles in a semicircle equal to 90 degrees. And that is the semicircle theorem. Semicircle theorem. Semicircle theorem. And then we had angles in the same segment are equal. Angles in the same segment are equal. Now that is the bow theorem. The bow theorem. And then we have angle between the radius and then the tangent equals 90 degrees. That's the radius tangent theorem. The radius tangent theorem. The radius tangent theorem. And then finally, angles between tangent and chord equal to angle in the alternate segment. So that is a alternate segment theorem. The alternate segment theorem. So this brings us to the end of the final section on circle theorems or the angular properties of circles. In my next section, we are actually going to just solve questions, purely questions on circle theorem. Thanks once again for joining the lesson. It's a great privilege coming your way with a nice lesson of that nature. Kindly keep on subscribing and then supporting my YouTube channel. And as I said early on, you can join the Telegram channel for live lessons when I start lessons on that. Thank you so much, and God richly bless you. Have a nice day. Bye-bye.